Hi everyone. So I'm very happy today that my first journal paper is published in IEEE transaction of biomedical engineering, and I'm holding the paper. Sorry, you cannot see it. It's blurred out. But the whole paper is about building um, an interpretable medical AI solution for a specific disease called hydrocephalus using low-field MRI. So the keywords are very important. So the name I have kept it GLAPAL-H, G for global, local, and parts aware learner for hydrocephalus. The H is in GLAPAL-H. The H stands for hydrocephalus, and the GLAPAL stands for all these individual elements of global, local, parts, and learner. Now, why I am so excited about this project? That what I have done in this project, this is what I want to tell you in this video, okay? So that you can also build a similar thing for other diseases. So to me, interpretability is very important. Whenever I have got this, I have encountered this problem from the very beginning, I wanted to make sure that it's interpretable. It's interpretable. It's not like you take one model off the shelf, train it, and it will give good results. But I wanted to make sure it's robust. It has good performance. Three things I believe are very important: good performance, robustness, and interpretability. So these three things are very important for me when I'm doing medical AI research, and I have made sure I put my whole effort into making sure that this is present in this work. And I'm going to explain you how I have done it so that you can also do it in your own work. Okay. So let's quickly understand. It will be a short to the point meeting. You can understand the mathematical details by looking into the paper, by reading the paper. That's not the most important part. The most important part is the idea of what and how you're going to tackle the problem, identifying it. So let me first introduce you to the disease. What is a disease? So in this disease, hydrocephalus, um, first of all, the disease is very deadly. It happens, there are around 0.4 million pediatric cases every year. 50% of them are from sub-Saharan Africa, mostly due to environmental reasons and other aspects. And interestingly, 60% of them of these cases of hydrocephalus happens by infection. So what happens in this hydrocephalus? So what happens is that you can see the brain here, and the brain uh, has something called ventricle, okay, inside. So what happens is that there's a duct through which CSF flows into that ventricle, and that duct gets blocked due to many reasons. It can be due to tumor, blood clot, or infections, which can be which can lead to pus, and it can get clogged up in that um, region, and the CSF, the fluid, gets stored in that ventricle, and that's why you can see that the kids have this large heads, and it's excruciating pain for the kids having that amount of fluid pressure inside the head. You cannot imagine. But the interesting thing is that most of them happens from infection, and like 60% of the cases. Now, why we're interested in this infection versus non-infectious cases? Now, I'm explaining you this entire disease because this is to tell you that building an AI solution is not just about performance, it's about understanding in medical AI. It's about understanding the disease and building it for the doctors, not just showing you are getting 99% accuracy. Okay, that's not how AI will help in any way in medical AI. So we have to take our time to understand what disease is doing. Okay, coming back, 60% of these cases are happening due to infections. Now, why are infections important? Infection is very important because the way the disease is treated, how it is treated. So there are operations of the doctors do, surgeons do, neurosurgeons do on the brain, where they drain out the fluid out of the child's brain, skull, from the ventricle. And it's also, there can be infections due to the complications due to the surgery as well. Any surgery is always risky. So if you know that it's because of infections what you can do is that you can treat it by an antibiotic. Okay. And that will totally reduce the cost of surgery and the complications and the risk associated with the surgery. This is why this problem is very important, to understand why infection detection is important. Now, how do we usually detect infection? Let's say we got malaria, dengue, or any other infection. We usually do a culture test, blood culture or fluid culture in this case, and we take it to the lab and they can understand, do some PCR, see there is an infection, and then send us the result, send back the results. But this is very time crucial for the kids. It's very deadly, as I said. So we need to do it fast. So a faster way to do is looking at the images, like at least not a faster, like it's not a foolproof way, but a decent way to understand what's going on inside the brain is to look at the imaging, the brain imaging, right? So that's why uh, previously we used CT scan. CT scan is the to-go modality of the disease. So to-go modality for the medical imaging of the disease. But CT scan have a few, like in resource constraint areas where there are less resources, CT scans causes a few issues. First of all, it's very costly. Okay, it's around $2 million. This is a number on average. I mean, this is not always like not like the whole range, but CT scan is costly. What I mean, and also CT scan has a cancer risks in babies due to the radiation of the CT scan. But the image quality is really high. But now there's a new device called Low-Field MRI scanner. This is a hyperfine low-field MRI scanner. It got approval of the FDA. Now, this can also be used. Researchers have found that for hydrocephalic cases. And the good thing is that there is no radiation, and the cost is almost 10 times less. And also, the the challenge is that the image quality is very low, as you can see on the screen, compared to the CT scan. Now, what people have seen is that imaging can be a really good way, a proxy for detection of infection versus non-infection. So this is the problem that we are trying to tell you. So PIH is a short name for the post-infectious hydrocephalus infection, and NPIH is for non-post-infectious hydrocephalus, that is the non-infectious. And we have also healthy patients. So this will tell you about the data set that we have, and also what problem we are trying to solve. So the goal is to detect the infection, okay, the PIH. And as you can see in the PIH versus NPIH, let me explain to you what these pictures are denoting. So in both the cases, the darker region is the brain, and the gray, the dark region is the CSF, and this gray region is the brain. Okay, the brighter region is the brain, and the darker region is the fluid. So as you can see in this PIH, the infectious case, it's very erratic. It's very different than this NPIH cases. And this is the normal image, the healthy patient. So you can see how much fluid it has manifested, has grown inside these ventricles. So what happens? So what we have observed, what the researchers have observed, that in most of these cases of PIH, there is this asymmetric structure with calcifications, which is only in CT scans, by the way, abscesses, loculations, all these things. These are names for all the whole asymmetry you see in this picture. And also their debris, you can see, for example, their debris out here inside the black thing, which make it feels like it's harder actually for the imaging. So the disease manifests itself in multiple ways. Okay, but the visual manifestation is very different in PIH versus NPIH, as you can see. PIH versus NPIH, you can see visually. So that's why the medical professionals, the neurosurgeons thought of solving this problem. Can we detect PIH versus NPIH versus healthy using a computation algorithm using low-field MRI. So work has already been done on with using CT scan by our lab, but we wanted to know that can we do it by low-field MRI, because low-field MRI has a lot of advantage and it has low quality. So can computation help us in that? So that's the problem I'm trying to solve. Now, the way to solve this problem is you can take a model out there and fit it and see and say that it's working. But I wanted to make it more interpretable, more robust, high performing, and also in all these three things: high performing, robust, and interpretable. These things are three things are really important to me. So how we have built it? To build it, we need segmentation. I will tell you why we need segmentation. So we have used ITK snap to segment it and to for the FLIR ground truth image. So yes, so we have low field MRI image and we have done this whole segmentation with the ITK snap by manually editing it. So now I will explain what interpretable methods I have, how I have developed this interpretable method. And this is my approach of any domain-enriched interpretable method for medical AI. Okay. For any disease. And I have specifically applied this to hydrocephalus. So you can do it in your own way for any other disease. So I believe this structure is very important for people to build solutions. So when a medical professional looks into the imaging of a disease and trying to understand what's going on, the medical professionals, as I've collaborated with doctors and biomedical engineers, radiologists, I've understood that they look into three core things. Number one, what is the imaging modality? CT scan, MRI, they C2 MRI, T1 MRI, FLAIR MRI, low field MRI. Also it can has FLAIR T2. But this manifests itself in different ways. Okay. So we need to understand that which organ is actually manifesting in, or which part is manifesting in what visual intensities. Therefore, imaging modality is important. Then human anatomy is important. When you're looking at an image, the doctor thinks, oh, this is this part of the brain, this is this part of the brain. So the human anatomy is important. Doctor is internally thinking this. But we need to make an AI model trustworthy so that it can collaborate with the doctors. We have to make it think like the doctors. So we have to understand how the doctors think and incorporate into the model. And the disease etiology is how the disease is manifesting in this imaging and with the correspondence of this human anatomy. So this three information and their collaboration is very important to be baked into an AI model so that it can learn well, mostly in resource constraint areas, to have a more better performing model in resource constraint areas. It's like you will not be able to have millions of data set of this. Okay, like the MNCs have. We have low data set and we have to adapt our AI model with that and make sure our AI is robust, high performing, and interpretable. And that's why we have built this GLAPAL-H. So what is this doing? So it's in this human anatomy, it's looking into this segmentation. So it's the mathematical model of human anatomy is nothing but segmentation. So going back here, when you're segmenting here, essentially you are saying that, hey, this is brain and here this is fluid. Okay. So that's what segmentation model is telling it to the model. Just like the doctors think in their mind, similarly, it's telling it to the model mathematically. Similarly, using the architecture, the model architecture, and the regularizers, which we will learn, we are actually looking for disease-specific measures. Like in this case, as I said, that there are abscesses, loculations, debris. So here it's actually my architecture will actually look for this large-scale asymmetry, dilation, loculations, all these things in this anatomy, okay, in CSF and brain tissue. So this collaboration is very important. And that's what I've tried to build in GLAPAL-H, global, local, and parts aware learner for hydrocephalus. Now, I'm not going to go in each of the details. You can learn these mathematical details because it's for a general public. You can learn it from the paper and let me know if you have any doubts or questions. I would love to explain it to you. But overall, this is the whole idea. The idea is when I am inputting a low-field MRI scan and it has three branches. The global branch, as I said, okay. the global branch, which is extracting the global etiology. Like there's a large scale asymmetry, as you can see here, a global etiology, large scale asymmetry between PIH and NPIH. Sorry for moving it. So let me explain you again. We have the global etiology, large scale asymmetry of the brain, and we have the local etiology. Okay, we are looking for local information out there, but this should be guided by, when I'm saying the global etiology, it's like you're looking at the brain from a distance without knowing, hey, here are the organs, but you can see that, there's an asymmetry and large scale um, distribution difference, intensity distribution difference, spatial distribution difference, without looking into the specifics. Okay, we also look like that. That is what we're capturing the global branch. In the parts, in the segmentation branch, we are actually doing segmentation and capturing the anatomy. And then once we do with the anatomy, we use the anatomy to look for local information out there, like abscesses, loculation, septations, debris, local information, just like doctors think and see. So human beings think and see in two ways: global way, like it's like you squint your eyes and then you don't know exactly what it is, but you can understand that, hey, this is, you can understand the overall structure. That's what we are doing in global branch. And local branch is that you're zooming it into it, looking for specific regions of the anatomy, because different things in the anatomy means different things. So, and then looking for specific markers, and then we use this global information and local information and fuse them together to get the final prediction. Okay, so this is how we are building the model. So one important thing, one architecture wise thing is very important, is to make sure it's local. Everything else is very simple. It's made of very simple aspects, but the combination of the simple aspects is very important. For example, in local branch, what we have done is that, this is very technical, is that we have made it four layers. Okay, so that it doesn't, the receptive field of the convolutions is less. This is a very important in the engineering aspect, that what we have done. But in the global resin 18, we have had the 18 layers, but here we don't have the 18 layers, we have only 4 layers. Okay, so this is very important to understand. So if you even consider this encoder and this encoder, it's like probably 6 layers, or 6 layers. Okay, so it's very important to understand this, that how we have made the engineering changes to make it look like a doctor. So you should read the paper and understand what we have done along with the mathematics. So for example, we have local losses here, regularizers, which captures exactly those local informations using contrast based aspect. We have global regularization so that we can squint our eyes. So when we squint our eyes, we somehow smoothen the image, right? And that's, there is a global loss out there, total variation loss. So, and there's a parts loss, which is kind of saying that, hey, look into brain and look into, it's a segmentation kind of loss. And then finally, loss of prediction, the cross entropy loss. So the most important things are 3 things. The global loss, which is kind of making you squint the eyes and looking at the overall global structure. I have used the total variation loss. This is again technical, this small technical detail for 1 or 2 minutes. Local loss for extracting those local specific information out there. Okay, like abscess, loculations. There's a mathematics. I have used contrast based loss because those things come up with contrast. When doctors were telling me that, hey, this is abscess, this is loculation, I was saying that, oh, this is high contrast, and they said, yes, this can be mathematically modeled by that. And then parts based loss and segmentation loss to actually guide you towards those brain and CSF. Okay, and we have added this loss together. Okay, coming back again, 3 branches. One is taking the global information and local information, and then there's a parts based information, which is the anatomy guided. Okay, so if I tell you about, if I make you understand what is the global and local, this is how it looks like. So let's say you want to compare SUV versus sedan. You can understand that there, when you look for two, like when you, as I said, when you are looking for 2 things, when you are differentiating 2 images, visually you have 2 information actually. One is the global information, like as you can see, the body size of front and rear design, and but the local information like a logo, okay, the headlight, the tires, all these things are local information. Similar to here, you can see that NPIH has large scale, PIH has large scale asymmetry compared to NPIH, as you can see on the screen on the left hand side. PIH has large scale asymmetry. That's a global type of thing. And Local is, as I said, abscess localization. All the green markers are the local information, okay, which captures the local information. One important thing to understand here is that the losses here, L1 and L2, are made in such a way that the local and global information are complementary. They do not capture the same thing. Okay, that's how it is made. And you will see it in like interpretability, how it's manifested. This whole engineering has actually helped in the better interpretation. So now finally, after this prediction, we do a patient-wide prediction by accumulating the middle 50% of slices, because that's where the most information is, and then averaging out and doing, if it's more than 50%, it's PIH. So this is important. Let me show you the results. To show you the results and experiments, I have to tell you what experiments I have done. So I have done two experiments mostly. One is two-class problem, that is predicting PIH, NPIH versus NPIH, and three-class problem where I'm predicting PIH, NPIH, and healthy patients. So there are around 28 PIH patients, 19 NPIH patients, and 26 healthy patients. Yeah. So one important thing to note is that since it is scan gives out a lot of radiation and it's harmful for the babies, we have no healthy CT scans. Okay, we don't have that. So the red part, that is the flare, this is used for NPIH, PI, and healthy classification problem. So I'm calling it a 3-class problem. And PI was NPIH, I have both CT and flare and like low field, and I have used both of them for the modeling. Now we have built GLAPAL-H, and it outperforms the set-of-the-art method for two-class problem. And one important thing to note for all the methods, I have described in the paper that why I have selected these methods, because this method, it actually encapsulates how computer vision has evolved over time with AI. First, there was just convolution layer CNN. Then there came vision transform best, and then there came conv next, which kind of uses convolutions but use the parallel structure of the VITs, the vision transformers. And then I have used RS2net, which actually uses segmentation guided classification, but ours show that we are actually, GLAPAL-H actually shows that it's better than all of them, because it has all this information of how the doctor is looking. These are off-the-shelf models out there, okay? One important thing to note is that CT scan, the top model for CT scan, that is Barnett CT, it's actually doing worse than GLAPAL-H. GLAPAL-H is outperforming that using low-field MRI. What does this mean? That means you can use low-field MRI for prediction, okay? And you can use it with higher accuracy. It has a 3% higher accuracy, and it still significantly outperforms it with low-field MRI. So you can have better performance and no radiation, which is caused due to CT. This is so exciting, right? And similarly, it also outperformed for 3-class problem. Okay. One important thing to note is that, again, you should read the paper, and I will show you those aspects, that when you add healthy patients to this set of PIH and PIH, it kind of distorts the distribution, right? It distorts the distribution because healthy patients are totally of a different kind. It's not hydrocephalus, but still it outperforms, okay? And we have made individual case-wise, label-wise analysis in the paper, and you should read it and understand that why it is. And finally, the interpretability, why it is important. I will show you the pictures and why it is important. But finally, the favorite slide of mine is this, is that how doctors look into this image. You can see on the left-hand side, original image, and how our model looks into it. For example, the Barnett and Mednext, you can see the infection, it's saying that it's all over the brain. It's not very specialized. But you can see GLAPAL-H looks into local and global, and you can see how they are distinct, right? How they are complementary each other. Whatever is present in global is not present in local, and vice versa. So statistically speaking, so when you combine them and get this, you can get a rich information of why the infection and where the infection is happening. And it turns out that, see, there is necrosis, and it turns out it's actually lighting it up. There's inflammation, and it can see that it's actually lighting it up, okay? And there is also debris out here, it's actually lighting it up. Similarly here, there is abscess here, and it's hugely lighting it up. So this is where the enhanced interpretability is coming, because we are mathematically modeling, we are actually visually mimicking, mathematically mimicking the doctors, okay? And this not only improves the model performance, it gives interpretability and it also gives robustness. So I will show you that how it gives robustness. You can go to the code. I have kept the code, the whole code out there. You can check it out, and you can go to the go to the IEEE paper, and we also have a free version of it. I will show you that there are a few more things. One is we have shown the robustness. So we have shown that PIH, even if we add these healthy patients, the PIH accuracy, the infection diagnosis, the infection detection rate is not decreasing, but it's decreasing really highly for the other models. Okay, for GLAPAL-H is not reducing. I'm just telling you the idea so that you can go and this is go and check it out. So this is the robustness analysis. So I have shown you robustness, and also you can see here that the PIH detection rate has actually not changed here, as you can see for GLAPAL-H. For all others, it has changed, and it's not good. It's not good. It doesn't tell you that it's robust. So our model is actually very robust, and we have proved it. So we have shown high performance using this. We have shown high robustness analysis using this picture, and we have shown high interpretability. Also, for resource constraint results, we have shown that even if you use 40% of the training data set, we are achieving 86% accuracy with just 40% of the data set. Why? Because see, we humans learn from less data. We do not need large amount of data. So the more human mimicking systems you develop, the more interpretable it will be, the more robust it will be, the more high performance it will be, and hence it will be learning from less data for this exact problem. That's why I am so in favor of showing off interpretable methods, and I have sweated a lot for building this algorithm. Okay, and I have told you the secret how to build it. The secret is simple. You can do, and I wanted to build for every and other disease. Secret is to understand and bake all the three informations into your AI model. Okay, and mathematically understanding it. That's why core computation understanding how imaging looks is how the imaging characteristics is mathematically baked into certain basic image processing aspect is very important, because that's how you build the regularizers. That's how you build the network architectures. Okay, so I hope you enjoyed this. I have made everything out there, open out there, so you can go out there, read it, look into the code, implement on your data set, and reach out to me if you have any questions. Okay, I would love to help you out and make you understand, even help you out in building it for your own model. So this is the core slide for your model. Go ahead and build interpretable medical AI solutions, and not just off the shelf, because we don't have millions of data set. Okay, and I want you to build that. So I'm very happy to share my ideas with you with this paper, and I'm so happy if you have stayed till the end. Thank you so much for staying till the end. And if you have any ideas, any thoughts, please feel free to reach out to me. I would love to talk to you. Okay, thank you so much. Have a beautiful day ahead. Bye bye.